This video is supported by Neogen. More about them later in the video. Hello and welcome back to the Genomics Bootcamp. This time we will be speaking about a software called SLEMM that is used for genome-wide association studies. On the screen, what you see is actually the publication for SLEMM in bioinformatics that was published in 2023. As always, it is a good idea to start from the actual publication for the software because, well, you can get the basic idea what the software is capable of. In this video, we will focus solely on its genome-wide association capabilities. The software is freely available and it can be downloaded from the website, from GitHub. And so the link is also in this publication, but I will also put it in the description below. When you follow the link for the GitHub, it lands you on this page, which has all the necessary files and also some documentation and description. On the website, you will find more information to the installation or the necessary software background you need to have for running SLEMM. Then on some of the options or capabilities it can do, and some example use. Now I have to admit that for me it was a bit of a challenge to run this software. I found out a way how to do it via trial and errors. Therefore, it can be that there is also another way to run things, especially running the compiled executables files as opposed to the Python scripts that are provided. And well, I will talk about this more later. But for this demonstration, or well, with this rundown, I decided to go with the version of the pipeline that worked for me. Before you actually can run SLEMM, you need to prepare the phenotype and genotype files. This preparation process is individual for your case, so I cannot provide a copy and paste kind of script that you can readily use. Instead of this, what I will do is I will go through the files that you need to have and also show them how they look like, and then you can prepare your files accordingly. I have to mention that SLEMM and also some of the follow-up processes require Linux environment. So, well, this one you need to have to run SLEMM. So first things first, you need to download SLEMM. This can be done from the website or from the GitHub when you go for installation, releases, and then here you have the SLEMM version linux.zip. So basically you download this, unpack, and there you will find the SLEMM executable file. It will be called simply SLEMM. In addition to SLEMM, you will also need a specific Python script that is also provided by the authors. You can get this Python script again by clicking on the installation, and then on the left side here there is a directory called bin. So you click on that, and basically, well, you can download here both Python scripts. One's called SLEMM_gamma.py and the other one is SLEMM_GWA.py. So we will actually need the second one, but there is no harm to actually download both. In addition, you will need Plink 1.9 that you can download from the Plink website, and also Plink 2, so the actual Plink 2.0 program that you can download also from the Plink website, but you have to go on the top row here and click Plink 2, which gets you to the Plink 2.0 website. Here you have also the appropriate executable file. Please note that you will need the Plink versions for Linux. So if you download for Mac or Windows, this will not work. Well, technically speaking, you can also do the Plink preparations in Windows, for example, but actually it makes a little sense to kind of move back and forth from one system to others. So my advice would be to download the Linux versions and do everything on one spot. So with the files downloaded and everything being in one directory, so basically the Plink, the Plink2, the SLEMM, and the SLEMM Python scripts. So one thing that you probably need to do is to make some of the files executable. This is a specific thing for Linux, because if you copy the files there, most likely you cannot run them straight away. So you need to make them executable by typing into the command line chmod +x. So this is just to make them executable, and then the file name. So you do this for SLEMM, for Plink, and Plink2. The second thing that you need is your actual genotype file, and this has to be in the Plink binary pet format. If you have it in other formats, what you can do is use the --make bed Plink option, and that will create the BIM, the FAM, and the bed file that you need for this run. In addition, what you need is the so-called pgen files. These are specific files for Plink2, and actually this is maybe the most tricky part of the run, because well, one thing that well, obviously I also used the tutorial for this, well, for my first run, and that one you can look up on the examples page. And when you scroll down here, you find yeah, basically the LMM and GWAS, so the genome-wide associations, and basically this is everything that is provided here. So I have to say that the description for how to run SLEMM is a little bit sparse, and therefore it can lead to, well, some surprises down the line. And one of the surprises is that is actually not stated anywhere on this GitHub page, or at least I didn't find, that this P file actually has to be the genotype file format from Plink2. So what you need to do is actually do this, and well, for this one you can do it very easily with the Plink2 executable file. You can start from your binary pet file that for me it's called the GWAS data here. This particular run that I did was on cattle dataset, so I have --cow here, and the actual Plink2 option that makes the files that we want is the --make -pgen. So similarly to make bed, makes binary pet files, the make pgen makes these pgen files. And I call this GWAS data _ Plink2 just for a good measure to distinguish the files from Plink 1.9 and Plink 2. Okay, so with this one done, one other thing that you would need is the so-called snip info file that has to be in a, well, CSV format, but technically it's just one column, so it doesn't really matter. This one you can extract from the BIM file. So, well, first, what I would suggest is do the quality control, and then from the quality controlled file that you will use for the GWAS, then from that BIM file you can extract this column using this small script. So you read it in, well, I use it with tidyverse. So I load tidyverse package. Then with the read table, I load the GWAS data, and then select x2 column, that is I call a snip here. So select snip equals x2, and then I write it out as a snip _ info.csv. And how it looks like. So as you see, this is, well, there is a header name and then just the snip names from the GWAS data BIM file. With this one done, you also need to then prepare the phenotype data file. And this is again very specific to your case. So what you need to actually do is a very simple file that has at least 2 columns. Well, it again should be comma delimited. And the first column would be the identification numbers of the individuals. And the column name should be PID. And then the second and most likely also the other columns are the phenotype values. Where I say is most likely because what I tried is just with one phenotype, but I suspect it works similar way as, for example, in GEMA, that you can have multiple columns with multiple phenotypes, because at some point you need to actually also specify the phenotype name, as you will see. But for the time being, or for this example, I keep it simple, and I have just one column with the phenotypes. How this file looks like. So I have here the pheno.csv. So there are 2 columns in this case. So the first column is the PID, so basically the ID of the individuals. From me, this is recoded file names, and also, well, the phenotype file name. So for me, this data is what I'm using is not publicly available. So I put it basically in an anonymized form. But for you, I suggest that you use some phenotype name or column name that actually very well describes what phenotypes you are running or what phenotypes you're considering for your genome-wide association study. So with this, we have the files prepared. So we have all the files and executable files in a working directory. There is the plink binary pet files in the directory. There are plink2 pgen files in the directory. There is the SNP info data in the directory. And also there is a file with the phenotype data in the directory. So we are ready to run SLEMM. But before we do so, let me tell you a few words about Neogen, who are kindly supporting this video. Well, Neogen is a company that provides an extensive range of high-quality, cost-effective, and customized genotyping and sequencing solutions and services for a wide range of species. Neogen has an extremely efficient state-of-art laboratory based in Europe, offering rapid turnaround times to empower your research-based decision-making. Neogen's high-quality array portfolio provides efficient testing to develop targeted predictions and research opportunities at an affordable price. Its custom GGP chips combine outstanding design and evenly spaced coverage of the genome with the SNP parentage marker and causative content. Key drivers behind all of Neogen's new chip design include unique SNP select software and a multiple objective local optimization or MOLO algorithm, enabling Neogen to choose the best set of SNPs with optimal genome coverage, recombination rates, and minor allele frequency representation. What's more, Neogen also genotypes on Illumina or Axiom public consortia and custom arrays on behalf of their customers. The future of genomic innovation is here with Neogen's DNA sequencing capabilities. Neogen has been a leader in the innovation of whole genome sequencing, which offers the most detailed view into your genetic program by evaluating every base in the genome and navigating the complexity of genomic variants that make individuals unique. Neogen also provides ChIM-seq sequencing with imputation for select species to augment genomic selection strategies currently in place, in addition to a new technology called InfiniSeq. Combining Neogen's world-class laboratory services with GenCo's imputation pipelines and advanced analytics platform, InfiniSeq delivers the necessary insight to confidently select superior individuals from breeding populations and research objectives. With Neogen, customers can also purchase whole flow cells and send them their libraries. The Neogen team is ready to assist with any genotyping or sequencing project, whether it is current or only in the planning stages. Also, a good news is that the viewers of the Genomics Bootcamp or whoever are informed about this possibility can also get monetary benefits in the form of a special offer from the company. So Neogen would like to offer viewers of the Genomic Bootcamp £100 off £1,000 spent on genotyping on their GGP arrays. So if you spend more than 1,000, you get 100 off. What you should do for this is only to fill out the form that is linked below, and also quote Genomics Bootcamp in the comments for this offer to access it. So don't miss out on this opportunity. So thanks again to Neogen for the support, and we are going back to the genome-wide association study with SLEMM. In the next few lines, we will actually do and perform the genome-wide association study with SLEMM, evaluate the results, and also then show how to visualize them. These lines are basically the adapted lines from the actual SLEMM website, so you can find them here. But what I did, I replaced some of the file names that are on the SLEMM website that are for the example dataset for the file names that I used for my actual run. Well, again, remember that this one, it needs to be put into the Linux environment, and directly you can copy paste it into the Linux command line. So we start with /SLEMM, and the / is for starting executable files, and well, we make them executable here. So if there is any problem, then well, just first thing to try out is to run this line. So the chmod, it definitely need to be an executable to be so that you can run it. So you start with the /SLEMM, and then there is a bunch of options. So we just go for the simplest of solutions here. So we say --LMM for the modeling, and then so we need to specify the phenotype file. So it's --phenotype_file. So this one, and then followed by a space and the name of the phenotype file. For me, this is simply pheno.csv. So this is this file, and you just notice that so it has this header, and what we have here is the name of the trait that you want to include in the analysis. So this will come here as the next one, --trait, what you want to use, and this should be the exact name what is in the header of the -- or the pheno.csv file. So these two are to specify the phenotype input file and the actual trait that you want to run. The --b file is the Blink 1.9 binary pet file name, and the --snipinfo file is the snipinfo file that is just holds the list of SNPs. So that was also prepared before. So again, there is the option name followed by a space and then the name of the file. For me, I like to keep it simple, so I just call it snip_info.csv. Then it's fairly standard --out. So what you want to do here is to specify the output file name. Again, I keep it simple, just saying results stage 1 SLEMM. That is my output file name for this step. And then because we are in Linux, and well, most likely there are multiple cores, you can use multiple cores for computation, which makes everything quicker. This you can specify the number of num threads. So this number of threads or number of cores that are used. I use 10, but yeah, you can use more or less depending on your possibilities. After this one is done and you've finished without errors, so then you are ready for the next step, and that is using the Python script. So here there are a few things to note. Well, first thing, just to get it out of the way, so you can again use more threads or more cores. You can specify it with this first line, with the export line, and then what you need to do is run this Python script. This Python script is written in Python 3. So just a short note, there are, well, I'm not really a Python person, but what is clear that there is Python 2 and version 2 and Python version 3. This script is specifically designed and written in Python 3. So if you have Python 2, it will not run, or, well, it will produce a bunch of errors. So you definitely need to have a Python 3 installed on your machine. Also, what it does, or how this script is set up, is that it considers each chromosome separately. So in my case, as I told you, I work with cattle data in this particular case. And cattle has 29 autosomes. And that's why I use a loop here. So, which starts from chromosome 1 to chromosome 29. So this will run it for each chromosome separately. So we use this loop here, starting Python 3 all the time, and writing the full file name, so the SLEMM_GWA.py. So again, there is, I think, some compiled SLEMM_GWA, probably executable files on the website. But well, I could run this program with the Python scripts. So, well, I just show you this one because I know this one has worked. And well, you have to have also this file in your directory with everything else. Now here comes the bit of a tricky part that is not really described on the website, and that is --p file, and this is the core file name of the plink2 pgen files. So you might remember up here, so we created this GWAS data underscore plink2 with the make pgen, and so you need to, well, first create this with plink2 and then put this one into this -p file option here. So this is something that is, but as I said, this was one of the main points I got stuck with for some time, but well, finally it worked like this. The next thing that you need to specify here after with the --SLEMM option is actually the results file from the first stage. So you remember here you used well, some file name. Well, you can use this one. Nothing wrong with using a very general one like this, but you need to then specify the output from the first step in here. So for this SLEMM option. So I'm sorry, it just jumped. So then again, there is --out, and then you specify the output file name for the second step. And as I mentioned before, so this whole thing is a loop. So it starts with 1, 2, 3, and basically 1 to 29. And you will have one file for each chromosome. So this is a very nice way to put it like this. So basically you have a core name dot chromosome, and then this $E will, or $I will put the actual number here. So you will have the distinct file names for each chromosome. And by filling these things in, you also run it in the Linux command line, and basically this step actually takes a bit of time, depending on your dataset size, but then it creates the actual GWAS results separately for each chromosome. The stage 3 of this process is just basically summarizing all the GWAS results into a single file. And here what you do is basically move or rename for the first chromosome, the file from the first chromosome, to a file that will contain all the results. So for me, I called it results for chromosome all.txt. And then from chromosome 2, because, well, you have the chromosome 1 here already, and the chromosome 2 to chromosome 29, you basically just attach each file to this big file with all the chromosomes. And at the end here, it also removes the actual partial results, just to clean up a little bit the working space. When you run everything, this is how the output file looks like. So it has, well, a header line, and then the most important columns are the first one with the chromosome, second one with the position of the SNP, third one with the ID of the SNP or the SNP name, and most importantly, the p-value, that is the significance value for each SNP for this genome-wide association study. One thing that I would like to note here, that, yeah, from my experience, that we want to then later on load this file into R, and well, this first line starts with a hashtag here, so this makes a bit of a problem. Certainly, this setup makes sense in some scenarios, but for our case, it just complicates things. So what I would suggest is just manually delete this hashtag here, so that you have a common name for the column. So you save and you are good to go. So what we will do is do a Manhattan plot out of these results. And for this, well, we will use R. And so this is basically the script that you might use there. So a little bit of tidyverse is necessary, or well, maybe not really, but I like to use it. And the other one is the QQman package that is very handy for doing Manhattan plots. So if you don't have these, then, well, certainly I would suggest to install. And if you have them installed, you need to load them. That is with the library tidyverse and library QQman. So you then load the SLEMM results. So I'll read them in. Well, I like to use the read underscore table. That does a very good job. And then you're almost ready to go. One thing that is nice to have is the some kind of a significance threshold. And one of these most popular significance thresholds is the Bonferroni. You can calculate it as the minus log 10 of the 0.05, which is the very often used or most frequently used significance threshold, divided by the number of SNPs. And in this case, the number of SNPs is just the number of rows in the SLEMM results file that is already, well, loaded here in the previous step. And the next thing that you will need to do is the Manhattan plot. And so you use the Manhattan function for this, which is from this QQman package. It's a very nice one. Basically, what you need to do is to specify the file with the results. In our case, it is the SLEMM results. And then you need to specify the important column names. For the chromosome, in our case, it's called chrom. So you just put it like that. The base pair position, in our case, it's called pos. The p-value in our case is also called p. So, well, technically you don't need to specify it, but I like to have everything on one place. So you just write it down. And the SNP names with the ID. So this is the ID column, stands for the SNP names. For the genome-wide line, you want to include the Bonferroni threshold, and then with the other suggestive line you don't want to use. So you just, well, just put a false or a F there. So this does a pretty nice Manhattan plot. And if you want to save it to the hard disk straight away, so, and this is a very good idea, especially if you do this in Linux, because then you can have directly the output in a nice picture form. So you can use, for example, the PNG option here. So you specify the PNG and the PNG function and the file name that you want to use. So in my case, it's GWAS Manhattan plot.png. So that is before the actual Manhattan run, and afterwards you write dev.off, open brackets, close brackets. So you write dev.off, that will then create and save the Manhattan plot on your hard disk. So this is how the Manhattan plot looks like for this particular run. Well, it looks quite neat, but of course the results depend on your actual data, on your genotypes and phenotypes. So this is the short presentation on the SLEMM software. Well, let me know how you like it, or if everything works as expected. Certainly, SLEMM itself has a lot more capabilities. So this was just a very simple GWAS run, but I think, well, this is maybe the most often used capability. So it makes sense to start with this. In the future, we might revisit this software and well, see what else it can do. For now and for this occasion, I thank you for your time and I wish you a very nice day.